Ya, estamos en YouTube. We're on YouTube, Mohammad.
Okay.
Profesor. Profesor,
¿Sí?
¿va a presentar a...?
Sí, no, sí lo voy a hacer eso.
Ya, estamos online.
Ya, perfecto. Gracias, Karina. Okay, we are going to start now. Good afternoon, everyone. Thanks for being here today at the presentation of the Mohammad. We have some people in Zoom and some people in YouTube. You are all welcome, and if you want to make some questions, you can either add it in the chat here in Zoom or in the chat in YouTube Live. So my name is Alejandro Tirachini. I am a professor of civil engineering at the University of Chile. And it's my pleasure to introduce you today to Mohammad Sadrani, who is a PhD candidate at the Technical University of Munich in Germany. He holds a Bachelor of Civil Engineering and a Master of Science in Transportation Systems, both from the University of Isfahan in Iran. And since the year 2019, he moved to Germany and he's based in Munich. We have been working together ever since because I am the co-supervisor of his PhD. So, and today he's going to talk to you about electric bus planning with a detailed energy consumption model application to Santiago. So Mohammad is going to have 35 to 40 minutes to make the presentation, and then we will have a maximum of 20 minutes for a discussion session and questions. So without further ado, you're going to start with your presentation, Mohammad.
Thank you, Alejandro. Thank you for the introduction. Hi, everyone. Thank you for joining us today. My name is Mohammad Sadrani. I'm doing my PhD at the Chair of Transportation Systems Engineering at Technical University of Munich. It's a great pleasure for me to be here to present a part of my PhD research on the planning of electric buses. Before starting my presentation, I would like to thank my supervisors, Professor Kostas Antonio, and also Professor Alejandro Tirachini for the great support on the research progress. So I'm going to present my work in three parts. First, I'm going to present a detailed modeling of energy consumption for electric vehicles based on the dynamic of electric vehicles. Then the energy model is integrated into the planning of electric buses as a mixed integer nonlinear formulation. And finally, we test the model application on a real-world bus corridor in Santiago, and I'm going to show you the result of numerical experiments. Several factors can affect energy consumption of electric buses. If I'm going to categorize the main factors, I would say there are two groups. In the first group, you can see the factors related to vehicles or driving conditions. For example, vehicle load, passenger load, vehicle speed, auxiliary services inside vehicles, for example, air conditioning, headlights, heating, in-vehicle displays, and so on. And in the second group, you can see factors related to road conditions, for example, road slope and weather, and so on. But as a very special feature in urban bus operations, we know that the number of passengers inside vehicle can change at each segment. Segment, I mean the distance between two consecutive stations, or we can say station to station trip. But we know that the number of passengers traveling inside vehicle can change exactly depending on demands for getting off and getting on at each station, or we can say alighting and boarding. So for example, in this picture, you can see the number of passengers inside this vehicle is 50 at this segment, but after loading and unloading events at this station, add 30 passengers boarding, minus 10 passengers alighting. So the number of passengers inside the vehicle is 70 at this segment. But we know that the passenger load can be significant. For example, you can imagine for articulated buses with a capacity of 130, in the case of running with full capacity, the passenger load can be significant. For example, can be about 10,000 kilograms.
¿Escucha, Mohammad?
In driving conditions and route conditions. Sorry?
Please continue. There was a misconnection, but now it's fine. Please continue.
Okay. So previous studies have mostly used a simplified fixed energy consumption rate without considering dynamic changes, both in driving conditions and route conditions. In this research, we are going to provide a detailed modeling of energy consumption. So we know that the energy consumption of electric buses can be affected by two elements. The first element is auxiliary power, which is required for running auxiliary services inside vehicles, such as, for example, air conditioning or heating, headlights, and etc. Auxiliary power usually is assumed to be fixed during the whole driving operations, but it depends on the vehicles. For example, it's larger for articulated buses compared to a standard 12-meter buses. But the second term is tractive force or tractive power. Tractive power is required for the movement of vehicles considering different resistance forces acting against the movement of that vehicle. So tractive force or tractive power is needed to overcome resistance forces. But what is important is tractive power can change during operations depending on driving conditions and route conditions. For example, it can be different when driving over uphill sections compared to downhill sections. In this research, we are going to provide a detailed modeling of tractive force, including 4 different resistance forces, exactly according to the Newton's law. So you can see tractive force. The first equation is aerodynamic resistance, and also you can see in the picture, aerodynamic resistance is related to the resistance of air when moving a vehicle along a route. So it depends on the density of air or bus frontal area, A here, coefficient, for example, drag coefficient, and vehicle speed. The second term is rolling resistance. You can see also here in the picture. which is related to the frictional force created between a road surface and the wheels of vehicles. The third one is grade force, which is related to road slope. For example, the force needed to go uphill or downhill. And the last one is inertia force, which is related to the changes in the kinetic energy of the vehicle when accelerating or decelerating. But what is interesting here, you can see 3 different resistance forces can be directly affected by the total mass of the vehicle, M, which can further
Lo perdimos otra vez. ¿Dónde estás, Mohammad?
Bueno, vamos a esperar que se vuelva a conectar el relator. Parece que tiene problemas de señal con el internet. Ahí está. Mohammad, no te podemos escuchar. Tienes que activar
Can
el
you hear me?
Yes.
Yes, now yes. Yes.
And can you see the slide?
Not
No.
now.
No? Let me share it again. Now?
So, yes, we lost you when you were explaining about that the mass has a role in 3 of the 4 forces.
From here?
Yes, from here.
Okay. So you can see 3 different resistance forces can be affected by the total mass of a vehicle, M. And we know that the total mass of the vehicle can include the curb weight of the vehicle plus passenger load. We know that the curb weight of the vehicle is a constant or fixed value, but passenger load is variable because the number of passengers inside each vehicle can vary at each segment. So in this study, we are going to capture such variations. But we know that in real-world operations, not only we see such variations in passenger load, but also in vehicle speed. For example, vehicle speed can be different at different segments, depending on the traffic condition at that segment. Or road slope also can change. But remember, in this study, we focus on segment-based resolution. So we consider segment by segment. For example, road slope can be calculated by the difference between elevation or elevation changes between 2 consecutive stations and the distance between them. And also, elevation information can be extracted from different data sources. In this study, we use digital elevation map, DEM data. But we can also provide data with higher resolution. Now, we have to translate the tractive force to tractive energy or tractive power. For this, based on the energy, based on the efficiency of electric engine, we can do it. The efficiency of electric engine is estimated based on energy losses at different parts when transferring the energy from a battery to the wheels. For example, energy losses at different parts like drivetrain, including gearbox, inverter, and so on. But another point here is when the tractive force is positive, we are in the phase of energy consumption. But sometimes the energy consumption is 0, or it's better to say the tractive force is negative. In 2 situations, the tractive force is negative. In the braking phase, when a vehicle is braking, and also when driving over downhill sections. But the point here is electric vehicles generally, or electric buses equipped with regenerative braking system RBS can take the advantage of recovering a part of energy when the tractive force is negative. I mean, in these two situations. So you can see ETA, or the efficiency of electric engine, can be calculated for two cases. When tractive force is positive, we are in the phase of energy consumption, or when the tractive force is negative, we are in the phase of energy regeneration. This is regeneration factor, which can indicate the level of energy which can be recovered by means of RBS. Considering this fact, ideally, the whole energy cannot be recovered because of some limitations, for example, battery limitations or energy losses in the recharging phase. So, for example, it's assumed to be like 60%. Generally, there are two different charging strategies in real world: fast charging and overnight charging. In the case of fast charging, vehicles are equipped with smaller battery size, but they can benefit from multiple charging events at different stations. But in this study, we focus on overnight charging or depot charging strategy. In the case of overnight charging strategy, vehicles are equipped with large battery packs to cover several daily trips, a chain of trips. So the most important point here is the weight and the price of battery pack can be significant. For example, the battery pack can be 4,000 kilograms. So in this study, we consider the price in vehicle capital costs, and also we consider the weight of battery pack when estimating load-dependent energy consumption. Here also you can see typical parameter for the energy estimation of electric buses. In terms of vehicle weight, we consider also the battery pack. Alejandro, can you hear me? Because my connection, okay. And yes. Also you can see other parameters like air density, etc. Now I'm going to show you the electric bus planning problem, which is formulated as a mixed integer nonlinear programming model. Without going into much details, I'm gonna quickly explain the main concepts behind the main formulations. For example, in terms of objective function, we are going to minimize the total cost, including user cost plus operator cost. User cost has two elements: in vehicle time cost and waiting time cost. And operator cost has three elements: vehicle capital cost, human driving cost, and energy cost. If you remember, we are going to estimate the energy cost for each vehicle at each segment. And also another equation which is more important here is waiting time. As can be seen, we are going to estimate initial waiting time in this term, and in the second term, we estimate the extra waiting time for passengers failing to board. For example, to estimate the initial waiting time, because we work on high-frequency bus systems, the random arrival of passengers at the stations would be a rational, common assumption. So the average waiting time is assumed to be half of the headway. But in the case of failing to board, passengers failing to board have to wait for the next vehicle. So the extra waiting time is equal to the whole headway. Another point here is we are going to distinguish between the value of extra waiting time and the cost value of initial waiting time, because passengers feel more dissatisfied with extra waiting time. Extra waiting time is perceived as a delay, unforeseen, unexpected delay. So passengers are
¿Se fue otra vez Mohammad? ¿Puedo seguir yo con la presentación? Esto es una suma del costo del operador y el costo del usuario para buses eléctricos.
Hola Alejandro, ¿cómo estás?
Hola, bien, Ricardo.
Tal vez proponle que corte su cámara cuando presente. En una de esas podría ayudar.
Eso le voy a decir. Y la pregunta, bueno, que está ahí, prefiero dejarla para que él la responda cuando vuelva.
Sí, sí. Yo
Sí,
igual
no,
me
sí,
tengo que ir como
eso
20
video.
para la una, así que quizás no me pueda quedar a las preguntas. Me excuso de antemano.
Ya. Bueno, pero la respuesta es que básicamente estamos considerando la posibilidad de que no todos los usuarios se pueden subir al primer bus que llega porque hay estocasticidad. Eso básicamente.
Esto cantidad la pasada, no es que el bus vaya lleno.
O sea, claro, el bus se llena, digo, o sea que estocasticidad en el sentido de que los buses no necesariamente tienen la misma carga, todos los buses.
Ya, pero es por capacidad del bus.
Entonces, el bus puede estar lleno y las personas no se pueden subir al primer
Ya,
bus.
ok.
Y eso,
Porque
y eso
consideren que es perfectamente regular el servicio.
claro. Y eso, sí. Y eso él lo pondera por 3,5 veces
Sí,
más
eso
que
es.
la primera espera. Y no ha vuelto todavía. Esto es raro porque yo tengo reuniones regularmente con él por Zoom y nunca había pasado que él se cae tanto o que tiene una mala conexión.
En Alemania se supone que deberían tener mejor internet
Me
que nosotros.
sorprendería, es que hay en esto de tecnología, hay varias cosas en las que aquí estamos más adelantados. O en realidad, de que allá están sorpresivamente atrasados, mejor dicho.
¿Sí?
De esa forma, sí. Ok. A ver, no lo veo. Algunos nombres conocidos acá, Yerko, Esteban Muñoz, hola, hola, Rodrigo Álvarez, hola, aprovecho de saludar, Amir.
Hola Alejandro.
Amir Rafe, hola, ACC.
Hola.
No sé qué.
Hola
Hola, Amir.
Alejandro.
Ariel Fuentes trabaja con nuestro equipo acá en Transtep.
Ok, perfecto. A ver si ha escrito algo este chico. No, necesitamos esperar un momento nomás. No pagó la cuenta de internet, no, te cortaran el servicio. Bueno, vamos a esperar unos minutos si no tenemos otra cosa que hacer más que esperar, porque debería volver, si esto es muy raro que no se pueda conectar. Ahí llegó.
¿Te aprovecho a hacer un comentario, Alejandro?
Dale.
Alejandro.
Yes?
Hi.
Ahí volvió.
Hello.
Sorry, here. Hi.
I think you could stop your video just with my voice, okay. And this may improve your connection. Is your signal? Your connection is weak now. Okay. Okay. So if you want to continue, it's perfect.
So I was here, yeah. Okay.
Yes,
in
please.
Terms of constraints. Okay. Sorry again. In terms of constraints, we have a 4 group of constraints. The first one is related to vehicle movement constraint. The second one is related to size dependence. For example, we know that the capacity of articulated buses can be different from standard buses. And in the third group of constraints, we model passenger flow constraints. For example, this equation is interesting because we consider time-dependent OD flows. So we are able to capture the spatiotemporal variations in passenger demand. And for example, using this equation, we are able to update the number of passengers inside each vehicle based on alighting and boarding demands. And also in terms of decision variables, wow. Can you hear me, Alejandro?
Yes, we can hear you well.
Wow. It's very, okay. So in terms of decision variable, we are going to optimize supply levels in terms of service frequency and vehicle type selection. For example, we have two options for operations, operating with 12-meter buses or 18-meter buses. So we define binary variable. We test the model on a real-world bus corridor in Santiago, and I'm going to show you the results of numerical experiments. We consider bus route 506, connecting the west to east of the city, and also you can see the road slope profile here. Mostly there is a positive road slope when moving from west to east, from terminal A to B, because of the connect to Andes mountain range located in the east of the city. And also we are going to simulate operating scenarios for morning peak periods extending from 7 to 10 a.m. In terms of solution approach, to handle the complexity of mixed integer nonlinear programming model, we are going to decompose the main problem into different subproblems which are easier to address, non-linear programming subproblems. For this, in the first subproblem, we assume the operation with 12-meter buses, and then we are going to optimize the service frequency in the operation with 12-meter buses. The same procedure can be implemented for 18-meter buses. And now, according to the objective function value, we know that the best solution or the global optimum solution is the solution which can lead to the minimum total cost. So this is the best solution. Operation with 12-meter buses at the service frequency of 38. And also in terms of computing time, each subproblem can be solved during 8 minutes. So the total computing time is about 16 minutes, which is a good, acceptable computing time for an offline design problem. I mean, we are working on tactical planning level. But note that we are able to consider the global optimum solution using the composition strategy. Now, I'm going to show you the trade-off established between different cost elements, for example, user cost elements and operator cost elements. As can be seen here, the user cost in red will be reduced with the increase of frequency, which is normal because of reduction in waiting time and dwell time at the stations. But here you can see the user cost is very high, significant, because here the supply level is not sufficient. So some passengers are left behind, which can significantly increase the user cost due to the high value of extra waiting time. And also for capital and human driving costs, you can see both are increased with the increase of frequency. It is obvious because for providing more frequent services, a higher number of vehicles and drivers are needed, which can increase capital costs and driving costs. But what is interesting is the energy cost is not monotonic, the blue one you can see, including two turning points here and here, in which the trend will be changed. For example, from increasing trend to a decreasing, and again to an increasing trend. But why? Why? Because here we know that the supply level is not sufficient. So vehicles in this part, in this increasing part, vehicles are running with full capacity with the maximum level of passenger load, which can increase the energy consumption of vehicles. But here we can see at this point, exactly at this point, energy costs will be reduced. We can say the balance of supply to demand will be started at this point, just started. And the energy cost will be reduced because of a reduction in passenger load per vehicle. Again, we see that energy cost will be increased, but why? Here. Because we know that a permanent part of energy consumption is related to the run of auxiliary services and also for the movement of curb weight of vehicles. Okay. And here we know that the supply level, exactly here, the supply level is much more than what is needed according to the demand level, which means that a large number of vehicles are running with unused or empty capacities. Occupancies are far below the capacity, but consuming energy for the run of auxiliary services and for the curb weight of the vehicles. So we see that the energy cost per passenger will be increased, again, per passenger, because we calculate average cost. Now I'm going to show you the average cost as a function of the demand. As can be seen, the average cost will be reduced as a function of the demand, which can indicate the economies of scale in any case, even if the energy cost function was not monotonic. As can be seen here, it wasn't monotonic, but again, we can see the economies of scale. Now, we are looking into how considering a fixed energy consumption rate instead of a detailed modeling of energy consumption rate can affect the optimal frequencies, the optimal supply decisions. For this, in the case of fixed energy demand, we consider 1 kWh per kilometer for 12-meter buses and 1.7 for 18-meter buses according to the literature. So we are going to quantify the loss of accuracy because of using a fixed energy consumption rate instead of the detailed energy consumption rate. You can see usually a higher level of frequency is suggested using a detailed model, or we can say optimal frequencies are underestimated under fixed energy consumption. For example, here, the relative gap loss of accuracy is about 13%. Now, we are going to estimate the energy consumption of vehicles at different segments of the route. For example, here we can see at this part, for example, from segment 44 to 60, we can see the energy consumption of vehicle significantly increased, but there are some reasons why. Because those sections are close to the central part of the city in which the demand level and also traffic conditions are higher, which means that vehicles are operated with larger load factor and also with lower driving speed, which can increase the energy consumption of vehicles. But what is very clear is you can see variations in the energy consumption of vehicles at different segments. Then, if we make a high resolution average, again, a high resolution average over all different segments, we see that the average energy demand is about 1.34. So, which is higher than the simplified fixed energy consumption rate suggested in the literature, in the work of, for example, Trochin and Antonio, 2020. So 34% is higher, which is significant. And usually in the literature, there is a lack of information in studies going to optimize the planning of electric buses. There is a lack of information especially local information about driving conditions and route conditions. We are going to perform sensitivity analysis on demand level and road slope using demand multiplier. For example, demand multiplier 1.5 can increase the basic demand level by 50%. What is interesting is we can see the relative gap here, the loss of accuracy. Can you hear me, Alejandro?
Yes, all good.
Okay. The relative gap here is 13%, but the relative gap here is 17, which means that the sensitivity of solutions to energy estimation method would be more significant at larger demand levels. Again, we see the same result in the case of sensitivity analysis on road slope. We see that solutions are more sensitive to road slope at larger demand levels. This result can highlight the importance of considering a detailed energy consumption model, especially for crowded and inclined bus corridors. And finally, we are going to perform a sensitivity analysis on the ability of regeneration for electric vehicles and try to evaluate the benefits of RDS in the operation with electric buses. What is interesting is regeneration factor. About regeneration factor, there are several studies to evaluate the regeneration factor for electric cars, but this factor honestly is not clear for heavy-duty vehicles, for example, for electric buses. But in very few studies, it is assumed to be 60%. So here we are going to perform a sensitivity analysis on regeneration factor from the regeneration ability of 20% to full regeneration ability. So we can see at larger regeneration levels, we are able to save energy consumption and also total cost, obviously. And also a lower level of frequency would be suggested because of energy savings. But this result is promising for future electric buses, especially for those which are designed with full regeneration abilities, or it's better to say with the maximum regeneration ability, because we know that the whole energy cannot be ideally recovered because of limitations, battery limitations, or also energy losses in the recharging phase. So to sum up the main results, I would say the energy cost function is not monotonic, and also we see that the increase of service frequency not only reduce passengers costs, but also the energy cost of vehicles because of a reduction in passenger load per vehicle. And also we see that ignoring variations in operating conditions can lead to biased solutions in terms of supply levels. And also we see that solutions are more sensitive to energy estimation method and also to road slope at larger demand levels. Thank you for listening. If you have any question, feedback, you can easily contact me at any time. I would be very happy. Thank you very much.
Thanks, Mohammad. Thank you very much for your presentation. So now we have some 20 minutes. If someone has a question or a comment wants to make, it could be in English or Spanish.
I just turn off my video to avoid any.
Yeah, hopefully it works. Yeah. Ricardo, please.
Hi, Mohammad. Thank you for the presentation.
Yourself, so he knows who you are.
You're welcome.
Very good talk. I was wondering, the data that you showed was collected a real data, or it's based on your function of consumption for the buses? When you show that the curve, that one, the 18, I think is the slide.
Yeah,
that one. When you see the energy consumption line as a function of the frequency of the buses, this is computed on the line, or is it based on your model?
exactly for one line, based on the detailed model. Yeah, based on our model, exactly.
So it's for your model. And,
Yeah.
and how you are accounting for stop and go situations on some part of the road? Because I think in those instances, you tend to require more energy, and it's hard to take into account on a more strategic level that you're looking at.
Honestly, we are not working on a strategic level. We assume a charging infrastructure is.
But you're not taking into account the operations on a link-by-link basis. You're only taking the slope. You're not taking the, I don't know, if there's an incidence on traffic and the bus need to stop and go for queuing purposes. How is that taking into account here, or is not taking into account? I want to understand them.
He's asking you, I think, Mohammad, if the speed plays a role here.
So you're assuming that the speed is constant all over the link, or the speed is varying across the link?
Maybe he's gone. Are you there, Mohammad?
That's a good strategy, but whenever you're asking.
Whenever you get a question you don't want to take, you just switch on. No, the speed does play a role on a link by link basis.
And you assume the speed is constant, or do you assume that there is how many stops do you consider per link, or there's no stop, only at bus?
No, it is. Is it the bus stops? No recuerdo exactamente cuál es el supuesto sobre la velocidad. Si es una velocidad constante entre paraderos.
¿Y pueden compararla ahora con los registros de consumo de energía real de los buses? ¿Tienen datos de eso? No sé si Rodrigo de repente sabe eso.
Sí, no hemos comparado con datos reales. Lo que él muestra son los outputs del modelo. Este 1.34 kilowatts es lo que él estima que es el promedio en la ruta 506.
Ya, perfecto.
Debe ser velocidad constante entre paraderos. Me parece que ese es el supuesto. Pero entre paraderos sí hay varianza de velocidad. No es una...
Sí, porque de ahí puede considerar el flow. Pero me tinca que cuando lo comparen con datos reales van a tener esta diferencia. No sé.
No,
that's fine.
So,
I have to leave anyway. Sorry about that, guys. But really interesting. To be continued.
So the question, are you listening, Mohammad?
Yeah, I can hear you.
So the question is how you consider the differences in speed due to different traffic situations along the corridor.
Based on historical data, we estimate the average vehicle speed for each segment. Yeah, but we're working on segment base because we don't consider the stochastic in vehicle speed, but it's a very nice and interesting aspect for future study. Yeah.
Está bien.
Thank you. Bye-bye.
You're
welcome.
Bye, Ricardo. Thank you. Que estés bien. All right. So there are any more questions or not? Here there are some questions. Let me read. I think the answer was already there, Esteban, right? It is what comes from the actual speed of the buses. It is not an optimization the parameter.
Yeah, based on historical data, yeah.
Exactly.
Cruise speed.
Un servicio con un alto índice de rotación, ¿te refieres a rotación de personas que suben y bajan?
Sí,
Versus un
sí.
servicio que se llena solo una vez.
Lo que los amarillos llamaban los pasajeros pernos.
Sí, aquí...
El bus siempre va cargado.
Sí.
Eso es un bus que se está cargando en diferentes momentos.
So, eso impacta en los tiempos de viaje, pero no en las cargas promedio. Mohammad, the question is what happens on a route when you have passengers that get on and off a lot. So they make short trips. There are a lot of passengers making short trips versus a few passengers that make a very long trip, such that the occupancy of the bus is the same always. But in one case, you have more passengers than the others because of the trip length is different. If this has any effects on the energy consumption.
Actually, I'm not sure. I cannot say anything, but I think, of course, it can affect crowding costs, of course, because in this situation, the number of sitting and standing passengers can be different, but I don't think it can affect the energy consumption pattern. I think it's the same as the pattern identified in this study because the total or the average passenger load is more important.
So there is, but there should be an indirect effect through travel times, because if you have a lot of passengers getting on and off, the vehicles are for a longer time on the stops, and then the travel time is longer, and then just for this reason there is a larger energy consumption. But yeah, but in terms of load, it is the same in both cases. So the effect of this variable is not playing any role on increasing or decreasing the energy consumption.
Exactly. Yeah. In terms of dwell time and the energy consumption during the dwell time, yeah, can affect exactly.
So yeah, here there are some people that work in a bus company. So if you go to, please, Mohammad, if you show your slide where the energy consumptions are, the 1.3 something is your average, right? Where is that?
High resolution average over all different
1.34. This is the estimation with Mohammad's model, that is the energy consumption in route 506 in Santiago. So this, yeah, we're not sure how far or close this is from the actual operation. If someone here has data or has information about this, it would be great to share it now.
Perdón, Alejandro, entendí que entonces no habría mucha diferencia de consumo por carga, pero sí por tiempo.
Sí, exactamente. Y la pregunta siguiente es que lo que con su modelo, lo que estima Mohammad es que el consumo de energía es 1.34 kWh por kilómetro para buses de 12 metros en la 506. Entonces, es eso lo que nosotros no lo hemos contrastado con datos reales. Y es... Ese 1.34 es un resultado del modelo colocando las tasas promedio de ocupación y la pendiente de la ruta.
Ok.
Entonces, mi pregunta es si hay alguien aquí en la audiencia que está trabajando con la operación de vehículos, de buses eléctricos en Santiago, que sepa si ese 1.34 kWh por kilómetro es, se acerca o no al consumo real.
Sí, nosotros tenemos estadísticas que tengo que revisar y poder darte una referencia. Pero hemos estado trabajando el tema desde la planificación, otra gente dentro de la empresa desde la operación. Y ahí podremos contribuirte con lo que nos autoricen a contribuir, digamos.
Ok, entiendo. Muchas gracias. ¿Alguien más tiene alguna pregunta o comentario en YouTube? No veo nada tampoco. Agustín Campos, el costo. So the question from Agustin Mohammad is if you use the cost of energy in Chile for your estimations.
Yeah, we have we take input parameters from the work of Terracini and Antonio for Chile, for the case of Chile, exactly.
So the answer is it is the cost of energy here in year 2019. So it is, yeah, so from the values are in euros per hour, and then you could make the translation to pesos.
Yeah, but that work is related to 2020, which was published. I mean.
Yes. And the demand, the data for with which Mohammad worked is from 2019.
Yeah, April, yeah.
¿Algún comentario más? ¿Alguna pregunta? Hartos nombres conocidos en la audiencia, los saludo a todos. No, because so the question is if you showed your average cost. So the next question of Agustin is about how the average cost compares with the fare. The fare today is like I don't know how the euros now, but it's like 90 cents of a euro. So what you will need to compare is now. Do you have Mohammad? Do you have a table or a slide where it is only the operator cost, the summation of capital, driver, and energy?
Yeah, capital, human driving, and energy cost.
Yeah. Do you have that number?
I think the minus the average cost is about 0.9 or 0.8 euro per passenger.
Yeah.
Average operator.
Yeah. So it is similar to the cost of a single ticket if the person does the trip only using one bus. No sé si quieres complementar, Agustín, si quieres hablar. No? Okay. The cost per kilometer of a electric bus it's lower than a diesel bus. The cost of energy consumption is lower than the cost of diesel consumption.
Yeah.
The bus is more expensive. Yeah. The bus is It's more expensive to buy, but the operating cost is lower, and it's significantly lower.
Yeah.
¿Hay más preguntas? Any more questions? Okay, if not, I would like to thank Mohammad for his willingness to share his work with us here in Chile. And yeah, maybe we are not sure yet, but maybe he will be able to travel to Chile at some point. So that's it. Y muchas gracias a todos por estar aquí y nos vemos en la serie de seminarios del Departamento de Ingeniería Civil. De hecho, la próxima semana, el miércoles a las 11, hay otro seminario que es de transporte y va a ser híbrido, va a ser presencial en la escuela y también online. Es una investigadora que viene a trabajar con Ángelo Guevara, que lo veo aquí también. Ok. Chao a todos, que estén bien.
Chao, Alejandro.